All right, guys, let's talk about phase changes. So we've talked about solids, liquids, and gases thus far. All right, we talked about those three states of matters. Let's talk about the changes. We go from solid to a liquid, liquid to a gas, solid to a gas, and backwards. So going from a solid to a liquid, right, that direction, right, we call that melting or fusion. And it takes energy to go from a solid to a liquid. So in our delta H, right, which is in this case, enthalpy of fusion, that's the energy required to take a mole of any solid substance into a mole of any liquid substance. That is going to be a positive value. We're going to have to add energy to do so. And then when we go from a liquid to a gas, we call that vaporization. Right? And that also is a delta H is positive. It takes energy to take liquid to a gas. And finally, you can actually go, for some substances, from wasn't an arrow, solid to a gas. And if we go from a solid to a gas, that's sublimation. And again, delta H, sublimation, is positive. Okay? All right. Now, there's another term that we're going to introduce here. And that is, of course, delta S is also positive for all these. What is delta S? We may or may not know what that means. That's entropy is technically what we're talking about. And think about the order. So when we talk about solid, let's just pick on water. Solid ice, solid water. Ice is, the water molecules are in place. They're fixed. They're not moving, right, relative to one another, right? They're not. They're still molecular motion, but they're not moving water molecule past water molecule, right? When the ice goes to liquid water, now the water can move past one another. So the order of the water is more disorganized, so to speak. And then when we go to a gas, water vapor, right, there's a lot less order. Those water molecules are free and independent to move. And so that's what delta S is. Coming up, there is a whole chapter that hits on delta S. Now, let's talk about the other direction. So the other direction in here, from a gas to a liquid, right, we know that's condensation. Right, and from a liquid to a solid, right, we're going to call that freezing. And from a gas to a solid, we're going to call that deposition. So everything in pink, delta H is negative, and so is delta S. All right? They're losing energy. So water, or any other compound or atom, molecule, whatever it is, as it goes from a gas to a liquid, it loses energy. Energy is released. And liquid to solid, same. Energy is released. From a gas to solid, energy is released, and it's becoming more ordered. Now, this arrow in black, vaporization, is the same energy as condensation. They're this positive and this negative for condensation, they're the same value, opposite sign, right? Because remember, energy is a sign, right, not a value. So 10 joules is 10 joules, whether it's going into the system or out of the system. That's the sign. All right, so we took up phase changes, right? That's what we have. Now, there are two options, right? We can change phases or change temperature. Right? And either way, Q, what's Q? Q, right? Quantity of heat. Think of quantity of heat. So that's the heat. How much heat? All right, and that's going to be in joules. All right. For changing a state, we have delta H, either F times the mass or delta HV times the mass. Or it can even be delta HS, right? It's the delta H times the amount, right? And so our enthalpy of fusion or vaporization it can be in joules per gram or kilojoules per mole. M, of course, this is mass. So we can have grams, or it could be the amount in moles. Or sometimes you have to go from grams to moles. Just depends what you have. All right? Those are phase changes, or changes of state. The other one, if we're changing temperature, MC delta T, right? Where technically delta T is T final minus T initial, right? If we're going to do it, right? So M, of course, is mass. Your C is your specific heat. And delta T is a change in temperature. All right, remember, specific heat is joules per gram degree Celsius. All right, so let's look at now water. All right, I want to look at water and its heating curve. Okay. And so a heating curve for water. All right. So in our heating curve, we have a y-axis, which will be temperature, and an x-axis that's going to represent, it needs to be an arrow, energy. All right, and so if we start off, all right, we can take, our example will be 10 grams ice at 0, no, I'll do 0, let's do negative 10 to 110. So we're going 10 grams of ice from negative 10 to 110, all right? And so if it makes you feel better, we can do that too, right? Okay. But I don't like to do that because it looks weird to me. So what we'll do is this will be, where are we writing? Negative 10 degrees Celsius. We get 0 degrees Celsius. We'll have 100 degrees Celsius. And 110 degrees Celsius. So it's not to scale. What state of matter is water at negative 10? Solid, right? And so if we start off with solid water, we're going to have to warm that solid water, right? And so we'd have no energy added. We'd start off at negative 10 degrees, and we're going to warm that water all the way up to 0. So that's step 1. Okay? Once we get to step 1, then water at 0 is going to melt. And that's step 2. All right? At 0 degrees Celsius. Now, we are in chemistry land, so of course everything's going to follow perfectly well like this, right? We're going to have these nice sharp corners and everything. Once the ice melts, once that 10 grams of ice melts, and we still add heat, it's going to have course, a perfectly straight line. Number 3, to warm the water. So step 1 was to warm the ice. And then step 4, we're going to vaporize or boil. And step 5, heat, steam. So that's the heating curve for water. All right, a heating curve for water. What are your steps? Well, step 1 was to warm the ice, and that is Q equals M, right? Specific heat of ice, and then the delta T of the ice, right? And specific heat of ice happens to be 2.1 joules per gram degrees Celsius. Now, if you're using a problem, make sure you use either your textbook or whatever reference you're supposed to be using specific heat, because they might give you into 3 sig figures. It might be a little bit different. Okay. 2, get a melt ice. Q equals delta HF times the mass. Delta HF for this reference is 6.01. kilojoules per mole. 3, warm the water. That's now liquid. Q equals mass, specific heat of water, delta T of the water. Right? And of course, C is 4.184 joules per gram degrees Celsius. Then we got to boil or vaporize. Q equals delta HV times the mass. And our delta HV is 40.7. Or 40, I have 40.65 written down. Kilojoules per mole. All right. And then finally, step 5. Warm the steam. Q equals M, specific heat of steam, delta T of steam. And the specific heat of steam, I have 1.99 written down. And that, of course, is joules per gram degrees Celsius. So if we were going to calculate the total amount of energy, we would add up all of these together, if that makes sense. We would add them all up and go from there, right? And so we can do that real quick. Let's do that. So the overall heat, Q, would be MC of ice, delta T of ice, plus delta HF times the mass, plus M, specific heat of water, delta T of the water, plus delta HV times the mass, plus M, specific heat of steam, delta T of steam. Now, what's our problem? I have kilojoules per mole for some of them and joules per gram. We have 10 grams of H2O, right? If I divide that by 18.02 grams per mole, right? So I do our 10 divided by 18.02, I get 0.555. Let's just call it 0.555. 0.555 moles. Now, technically 10 grams is 1 sig fig. Let's assume that we have 3 sig figs. All right, just for fun. I'm telling you that now. We're assuming that. So it should be 10.0 grams. in our ice. Okay? So now we can plug in some numbers. Q equals our 10 grams, our 2.1, and the delta T. Now, technically it's final temperature minus initial temperature, right? So it's 0 minus negative 10 if we do it that way. You can do it that way. You can keep everything as an absolute value. The point of this is that you need to know that we're adding energy to this system, and the system is the 10 grams of ice at negative 10. We're adding energy to this system, so no matter what, the system is gaining heat. So everything should be positive, gaining the heat, or this gaining heat for the system. So this change is 10 degrees Celsius. Right, that's important. We have to know the direction of the heat transfer. We got to kind of understand what's going on there. So now then, the next term, melting the ice, 6.01. I'm going to put times 10 to the third joules per mole, right? Because that's kilojoules per mole. All right, and times by 0.555 grams, moles. Plus 10 grams of water, 4.184 joules per gram degrees Celsius. And it goes 100 degrees Celsius, doesn't it? All right? Again, we're assuming 3 sig figs. 100 degrees Celsius. It goes from 0 degrees Celsius up to 100. Then we're going to add the steam. And the steam is 40.65 times 10 to the third joules per mole, and times by 0.555 moles. And finally, warming the steam would be 10.0 grams, 1.99 joules per gram degrees Celsius, and change of 10 degrees Celsius. All right, so we're going to do this up front. To warm the ice, it looks like that's 210 joules. To melt the ice, all right, I would have 6.01 times 10 to the third times 0.555. I got 3,300 and let's call it 36 joules. And then we're going to have warming the water, right? 4,184 joules. Plus boiling or vaporization, 40.65 times 10 to the third times our 0.555. I got 22561. Plus 199 joules for steam. And so overall, I'm thinking we're going to get, if I do this, Q would be 30490 joules, 3 sig figs, 30500 joules, or 30.5 kilojoules. All right, so that's what it would cost in energy to take 10 grams of ice at negative 10 degrees Celsius all the way up to steam at 110. Well, hopefully that helps for you guys. If you have questions, don't hesitate to reach out. Otherwise, we'll see you next time, guys. Take care.